Google DeepMind has come out with a new paper, and this paper essentially allows the transformer model to have a finite memory. So you give it a finite memory requirement, and it allows it to dynamically allocate how it's going to use that memory as it's sending tokens through the transformer model. It's quite an interesting model, and yeah, let's just go through it. So they call it mixture of depths, and that's because you allow the model to basically choose the depth, or basically at each layer you allow the model to choose um, which tokens that layer wants to utilize, and thus allowing each token to have different depths, I guess. So mixture of depths, play on of mixture of experts, because mixture of experts is used, the idea from it. So the big idea is you have this expensive operation. So perhaps this is a feed forward layer, or it's an attention layer. Like the attention layer, you have to construct this big attention matrix, which is an S by S matrix due to the queries and keys, or other K and Q, like that. And this is massive. This is big compute. Everyone knows the attention mechanism is expensive to compute. And the feed forward layer is also really expensive to compute. You have this big hidden state you have to compute here. So you have your feed forward, which expands it from D to 4D and then back to D. So expensive to compute these two operations here. So like in your normal transformer, you have your norm, if you're using pre-norm, and then you have your attention, and then you have another norm, again, if you're using pre-norm, and then you have a feed-forward layer. And these two operations are expensive, and the idea is if we have a set of tokens, maybe we have like the cat sat, I'm not creative, the cat sat on the mat. So intuitively, looking at this sentence, if I were to just give you cat sat on mat, you would be able to easily understand what this sentence means. Or cat sat mat, you would also be able to decipher what that sentence meant. The word the is pretty useless, so it probably doesn't have to be sent through this mechanism at all. It's a waste of compute, essentially. And the word on is slightly more important than the word the, but perhaps it's not as important as, say, cat and sat. So you can see how this idea can be utilized by the transformer. And the idea is, as you're sending this, you take the set of tokens, and before you send it through your transformer layer, so it's just your transformer layer, you evaluate the tokens and you pick which ones you want to go through. And specifically, you pick K tokens. So K is a parameter you set. This essentially allows you to allocate some amount of compute to send some maximum amount of compute for this layer. And this maximum amount of compute will choose the top K tokens. So perhaps we set K equal to 3. So maybe it picks the word cat, it picks the word sat, and it picks the word, I think I have all these. So mat. So it takes these 3 tokens, and specifically only these 3 tokens are sent through the transformer layer. And the rest are just sent through an identity layer. So the output becomes the, and then cat and sat are transformed. On and the are just sent to the identity, and then mat is also transformed. One thing to note is that the attention mechanism is, like, the compute is reduced quadratically, because the attention matrix is, you only have, it's reduced quadratically because every token you add increases it quadratically. So every token you remove also decreases the memory requirement quadratically. So if this was a 6x6 matrix, because you have 6 tokens, you would only utilize a 3x3 matrix for these 3 tokens here. So the memory savings you can get is quite a significant amount. And that also means the flops are utilized better, and that means that it'll be faster to do this computation in the end. So doing this has a lot of benefits. Now, one thing to note is that they basically model this as kind of like an interpolation. So if k is equal to t, where s is the sequence length, then this is a full transformer. And if k is equal to 0, then all these are sent through the identity, and that's a stupid just identity transformation. So what they're looking for is basically some optimal k, perhaps like s over 2, which gives you the right amount of compute. So, or basically a good trade-off between compute utilized versus compute thrown away. So speed versus accuracy. This has a lot of accuracy. This has a lot of speed. Basically a good trade-off in the middle between these two. That gives you good accuracy, like really still good accuracy while a lot better speed than the full transformer. And I guess this also gives you memory savings. So like I said, mixture of depths is a play on of mixture of experts. So what is mixture of experts? You've probably heard of this if you've read some literature on transformers or heard about it. How do you improve it? Oh, you just add mixture of experts. You always add mixture of experts. Mixture of experts is fantastic. Basically, mixture of experts is a way of adding compute or adding parameters while not necessarily having to utilize all those parameters. So in kind of the feed-forward case, which is the original case mixture of experts is used, in the normal case, you have a token, and the token is sent through this big weight matrix here. So d by d, this is a d-dimensional token, and you get out a token of dimension d. So it's just a transform. Now, all tokens are sent through the exact same weight matrix. You have s tokens, s by d, and all tokens are sent through the exact same weight matrix, d by d. And they're all transformed in the exact same way, using the exact same transform. Now, intuitively, that doesn't make much sense. Different tokens represent different things in the sentence. They shouldn't all be necessarily transformed in the exact same way. Even like this weight matrix has to do a lot of work. And it may be better to instead have multiple weight matrices. So these multiple weight matrices are called experts. So you have expert 1, expert 2, expert 3, and so on, where each of these are their own basically weight matrix or transform. This can be a feed-forward layer. It can be basically anything. This is just a function. In the simple case up here, it's just a normal linear layer, but it can literally be anything. And you'll see later we utilize these or an expert to essentially do this routing for us. So you have some set of tokens here, like this, perhaps 4. Yeah, we'll go with 4. Now, what you want to do is route these tokens to these experts in some way. And to do that, you use a router for each of you use a router. And the router essentially tells you how the tokens are going to be routed, or which expert they're going to be routed to. You could send all them to every expert, but then that's basically the same problem you had up here where it's just a big weight matrix essentially. So you want to make it sparse where maybe this token goes here, this token goes here, this token goes here, and this token goes here. So how do you do that? There's 2 ways to do that. There's either token choice or expert choice. So intuitively, token choice chooses every token chooses the expert, and expert choice, every expert chooses the tokens. So for token choice, if we have a token here, what you do is you have some weight matrix, your router, which is going to be, say, a D by E matrix, or E by D, however you want to write that. This is then multiplied by your input x, so R x, and you do the softmax around that. And this essentially gives you a distribution over your 3 experts, expert 1, expert 2, expert 3, and it has a distribution for how much that token wants to go to that expert. So maybe this is like 0.7, 0.2, and 0.1. And that means that this token basically chooses expert 1, and it's sent to expert 1. It is then multiplied or it's then sent through the expert1 transformation, so maybe the d by d linear transformation, and the output is then the transform token just through this expert. And you do this for all tokens, so you have a second token here. It then goes through the router, so maybe this is token x2, x1 here. So you do softmax of router times x2. It gives a distribution, and perhaps it wants to go through expert number 3. So it's sent through expert 3, and then you get the output here. So that's token choice. Expert choice is just flipping this. So if we have, say, 3 experts, expert 1, expert 2, and expert 3, and we have, say, 2 tokens, then each expert is going to have a distribution over all the tokens. So you have a router. You basically have a router for each expert, and you can think of this also as maybe just a d by e transformation. So it'll be a d by 1 transformation for each expert. We can just do d by e, where e is equal to 3. And this will be our router. So s by d. And you send each of these through this transformation, and you get out basically you get out this a distribution for each of the experts. So you get out a s by e matrix. Yeah, S by E matrix, and you do softmax over the S dimension as opposed to the E dimension. Yeah, same transformation. So in this case, each expert looks at every token. So it would look at x1 and x2, and it basically says how much does that expert want that token. So maybe it wants token 1, 0.3, token 2, 0.7. Expert 2 wants token 1, maybe 0.1. And 0.9, definitely to scale. And expert 3, perhaps 0.5 and 0.5. And we could just choose first one. Now, the way, I won't draw it like that. I'll draw it like 0.8 and 0.2. So in this case, tokens are sent. This first token is sent to expert 1, this is one sent to expert 2, and this one's sent to expert 3. No. This one's sent to expert 1, this one's sent to expert 2, and the first one's sent to expert 3. And then you just do the transformation. So these are the 2 routing mechanisms. Now they each have their trade-offs. So like the router is the same. You just do softmax on a different, you either do it over the sequence or you do it over the experts. So that gives you your router choice, or it gives you your expert choice. So the size of the router doesn't change. What does change is how this behaves. So with token choice, which is originally how this was kind of developed, there's a balancing problem, because maybe you have S tokens and all S tokens decide to go to expert 1. Then that means expert 2 and 3 are not utilized at all, and you basically just have this case up here with unused weights. So there's a balancing problem of tokens, and you have no idea how many tokens are going to any expert. So that's very annoying to deal with. The expert cases, usually what's chosen, it's a lot easier to deal with because you can allow each expert to choose the top K tokens. In this case, there's just 2. So top K doesn't matter unless like K is 1. But in the case where you have like S is equal to 512, then you can have K is equal to like 7 or something like that. And it allows it, then you know for sure that each expert will have 7 tokens. It'll always have 7. So you know the compute, and you know that every expert's going to be utilized. However, the problem is tokens can be underutilized now. So if K is equal to, say, 1, and we have 3 experts, then we can have at most 3 tokens being utilized, not 512 in our 512 sequence. This is an extreme case, but you can imagine it in some cases, the tokens may not be utilized at all, and that's a problem. But this problem's usually easier to deal with than this problem here. So expert choice is usually used, and they actually do use expert choice, and it it's way easier to use in the scenario that in mixture of depths. Anyways, these are the two methods used for mixture of experts, and yeah, they basically utilize this for mixture of depths. So how do they do this? Let's go over to the paper right here. So you have X here. X is going to be your tokens, your set of tokens. So that'll be S by D. And you have your router here. Now your router is a single expert. This is, you basically think of this, your transformer block, as one whole expert. So this is just expert 1, and you don't have any more experts. Now you then set K, so maybe K is equal to like 128, something like that. And you have expert choice. So the distribution is created over all S. So this would be X1, X2, so on, XS. And you have your distribution, your probability, your softmax distribution over your sequence of tokens. And then you select the top K tokens, and the top K tokens are sent through the heavy transformer block, while the other tokens are sent through the identity, and they're just sent through the identity, so nothing happens to them. And this is the basic idea. So you can see here, the idea is at every layer you have a expert router, and the expert router is going to choose some number of tokens, some K tokens. Actually, it layers this way. So at layer 1, you have some number of tokens that's preset, and you then just take those tokens, send them through the layer, and the rest are sent through the identity. And that's basically it. It's just the expert choice, where your expert is instead one expert, and it's sent through the transformer block instead of some other thing. Now, they define down here how that's done, and there's a very important note to make. I'll erase this. So yeah, let me just erase this there. So at every layer, you have this selection. So X, you basically have your router, and it chooses the top K. And if the token is in the top K selections, then it goes through this transformation. And if it's not, it's sent through the identity. The transformation is the identity. So this is the top K. And I guess this is the bottom S minus K. And this transformation here this is just your function. So this is just the transformer block. So you can think of this as like the attention plus the feed forward layer of your token. So of just your token. And this is just the identity, or this is just the skip connection. Now, the important part about this formula is here. So this is your routing weight. If I go back up here, let's say the second token was picked. What we have to do is we have to multiply the token by the weight. This selection is not differentiable, but you can make it kind of differentiable. It's kind of like a hack where you multiply the output of the expert. So say the weight was 0.65 of token 2. After you send the token through the expert, so this is our expert here, our expert, then you multiply the output of the expert by the weight. And that basically makes this part differentiable here. Rather, it allows gradients to flow. You always have to have the gradients flow. So the gradients flow through the network because of this. And it basically makes this routing differentiable. Now, does this make sense? Intuitively, it kind of does. If you look at the gradient of this weight, it actually does make sense. Say you pass a token through, and it has some weight. If the token, say, has a high loss, then, or rather, the low loss, then it'll increase this part here. yeah, if the gradient if the gradient flow is positive, then that means that this token is doing well and it'll increase the weight. Otherwise, it'll decrease the weight. So if you look at the gradient, it does actually make sense, this part here. So it's not just, it kind of is just slap on the weight and it adds some gradient flow, but the gradient flow does make sense and it changes how you would want it to change. If the added token does well, then it increases the weight, and if it doesn't do well, like if the added token isn't that good, then it either doesn't increase the weight or it'll decrease it. So the gradient does work out in an intuitive way. Now they make some notes over here. Yes, about why they choose expert choice rather than token choice. And intuitively looking at it, it makes sense. But they have some other reasons. So if you do token choice, or if you do expert choice, then you don't need a balancing loss because the token, you have the top K token, so you don't need a loss saying, oh, send tokens places evenly, and you also have one expert, so that doesn't make sense. But you don't need that. You don't need some auxiliary loss. The second thing is basically it defines an ordering. So they mention here the top K operation depends on the magnitude of the router weights. This routing scheme allows for relative routing weights to help determine which tokens most need the block's computations. Router can try to ensure that the most critical tokens are among the top K by setting their weight appropriately. So essentially, this gives you a obvious ordering. So if you do token choice, there's no obvious ordering among tokens because the probabilities are not related. But if you do expert choice, then the probabilities come from the same distribution, so it gives you an ordering of which tokens should be sent through. And then third, because we only route through two paths, a single top K operation can split the tokens into two mutually exclusive sets, one for each path, preventing the over or under processing problem mentioned above. So essentially, this allows you to have a compute limit that you set, which is very nice. And it doesn't have the over/under processing problem because it's just one. But yeah, it gives you this top K option because you only have two paths. You only have one expert, which allows them to define this max compute. Before moving on to the results, because this is basically their method, there is one major problem. And that has to do with the sampling. So it's kind of subtle, but if you look at how this routing works, it's not causal. If I have a set of tokens here, and I have a router, then you have to define, or I have a router or an expert that I want to send it through. Then you define a distribution over all these tokens. And this distribution relates all the tokens in the sequence, which is not a causal operation. Say we wanted to make this a causal operation on this token here. So let's say this is our token in question. Like this is the last token that we have when we cut off the sequence here. To train this in parallel efficiently, you can't just train it token by token. You want to train it on all tokens, but this operation is inherently uses all the tokens in the sequence from the future and from the past because it looks at every token in the sequence. I don't think they fixed the problem of these tokens being updated in a non-causal way. Looking at the gradient, looking at the gradient, like a simplified form of the gradient, the softmax operation, if you just look at one token, then it affects the gradient of all the other tokens. So if we take this token here and we backpropagate through this token, say this token was selected, then this token basically has signal that goes to the future tokens, which doesn't make sense because, well, which is not what you want because you want this to be causal, and the past tokens. So it goes to all of them, and that's because of the denominator. So I don't think they fixed that problem. And it looks like it works even without that. problem being fixed, but it's a problem I wanted to mention, that there's still a gradient I think there's still a gradient problem where the gradient isn't causal. You still have this bidirectional gradient because of the softmax operator. However, they kind of have this hack where they have the model they allow the model to be sampled in a causal way. So I don't think they fix the gradient problem, which may be a problem that needs to be fixed to make the model better, but they do fix the sampling problem. So you can sample this causally, assuming it was trained well, even though the training is not causal because of the softmax operation. The gradient is not causal. It goes through the whole sequence. So the way they do that is by using two different methods, or one of two methods. So the first method is, let me expand this. I think that's as much. So the first introduces a auxiliary loss that empirically affects the primary language modeling objective approximately 0.2 to 0.3%. So the objective is the loss is higher than it should, than desired, but not by a lot, but allows us to sample from the model autoregressively, which is what you want in a GPT model. We can use binary cross-entropy loss within the router's outputs to provide logits and top case selections of these logits. Sorry, I totally messed that up. Wherein the router's outputs provide the logits and the top case selections of these logits provide the targets, i.e. 1 if a token was among the top k and 0 if not. Intuitively, this loss centers the sigmoid of the router's outputs around 0.5. Those tokens are selected among the top k, are pressured to produce router outputs above 0.5, and those lower than the top k will be pressured to produce outputs below 0.5. So that doesn't make much sense. However, what it seems like they're doing here is if you have, say, 5 tokens, so you have your 5 tokens, 1, 2, 3, 4. Wow, that is a terrible rectangle. What you do is you send them through your router. So you send them through your router, and your router basically gives you this softmax distribution, your probability distribution over all your tokens. Now, imagine x1 and x2 are selected. So k is equal to 2. Then what you do is you create this binary mask. You have this binary mask here. What you then do is you send this through, so you sent this through a router already, and then you sent it through a softmax distribution. So instead of sending it through a softmax distribution after you got these outputs, you then send it through independent sigmoid distributions. So every one of these x's is sent through an independent sigmoid distribution. And you can then have a loss for the sigmoid of every token versus the k value or versus the 0, 1 mask. So this seems weird at first. I think the reason they do this is because if you have this routing here, the routing here is not causal. It's inherently not causal because of the softmax distribution. And the way you train it is not causal because of the softmax distribution. But if you train a sigmoid distribution, which is independent of the future tokens and the past tokens, to basically do a prediction on the top k. So this basically predicts, is this token going to be sent? So like both of these basically have the same task. Both of these basically say, is this token going to be sent to the expert? This just does it where it relates all the tokens, or this does it using a operation over all the tokens. This does it using independent operations. And this operation here, assuming it's trained well, will match this operation. And that allows you to do a causal sampling because these are independent. It's not messed up. The distribution isn't trained in a causal way. It's trained in an independent way for each token, just in a way that kind of mimics a softmax distribution. So that's the way I kind of think about this. You have your input tokens, you send them through your router, and the router then creates your softmax distribution, and this distribution will be used for training. You still use these weights to update your softmax distribution, and you then get your 0 and 1 mask. You then have a auxiliary loss in the middle of your network. So this part here is sent through the transformer. But you have this auxiliary loss, which basically is a way to allow this to be sampled using in a causal way. And you have these independent sigmoids using the same exact activations, which will try to mimic the softmax, or tries to mimic the goal of the softmax, this routing. And if it does that well, then you can sample using this procedure here. So you sample using this, you train using this, and you train the sigmoids while you're training the normal model. So this is just basically you slap on this part. Yeah, that's basically what they do. So hopefully that makes sense. You have these independent sigmoids, which are not causal. You have the softmax, which is causal. And since this is not causal, you can sample it causally, or you can sample it. Since this is not bidirectional, you can sample it in a causal behavior. So, yeah, you would use this for top K. You would not use this for top K whenever you're sampling. Yeah, so that's why they do these independent sigmoids. It can make it causal, or it's not inherently bidirectional. Not bidirectional. Now, the second thing they do is they have an MLP, which basically does this task. So these use the same weights. These weights are just sent over here to the loss, to the auxiliary loss here, sent through a sigmoid. This is basically just using an MLP to transform the weights instead of using the same exact weights. So a small MLP predictor, second router that receives the same inputs with a stop gradient, but whose output is a prediction whether that token will be among the top K or not in the sequence. This method does not affect the language modeling objective and empirically does not significantly impact the step speed. So you have a set of tokens here. That should be 1. You have a router. This is your normal router. This is under the softmax distribution. This is under the sigmoid distribution. This gives you your normal probabilities for your expert. You then send it through the expert. Now, you also send it through the second router here. And the second router is just the sigmoid router. So this is going to be your bidirectional. This is going to be a not bidirectional, independent sigmoids for each token. And you basically train this to just mimic this over here. So yeah, that's it. This is the same thing as what I described before, just using a different set of weights as opposed to the same set of weights. And that allows you to sample autoregressively because the sigmoid is not bidirectional while the softmax is. Again, I want to note, so this part makes sense. Hopefully since you're under a not bidirectional distribution, you can sample that causally. I still want to mention that the gradient itself is still bidirectional. So I think you're still solving it bidirectionally, implicitly or explicitly. I think you're still training the model bidirectionally because the softmax distribution sends gradient signal to all the tokens. So, and I don't think they solved that in this paper. I could be wrong, but I don't think they do. And I think that may be a problem, but not sure. So anyways, this was sampling was interesting to make it causal. Now what they do is they train it on the smallish model. I don't think they specify the exact parameters besides we use a cosine scheduler and we use training steps and we have a bat size of 128 and a 2048 sequence length. And I don't think they mention the other parameters. Do they have an appendix? No, they don't. So yeah, I guess we take their word. So some interesting things from these charts is overall it looks like MOD utilizes the parameters more efficiently than non-MOD cases. Now, before this whole paper, the big reason for it was to reduce basically set a compute limit. Now, they basically look at a bunch of different models and they find that the best way to allocate this, the best way to basically add these layers with the compute limit is to do it every other layer, interestingly. So instead of having what would this be? It would be an MOD layer. So you have your input, then you have an MOD, and you just stack this. This works a lot worse than if you do MOD and then a full layer, so a full transformer layer, and then an MOD, and then a full layer, and you just stack them and alternate between MOD and your full transformer. So yeah, every two. They mentioned that's the best they found. It's better than doing it every layer. Another thing they mention is that 12.5 capacity. So if you have a set of tokens, only 12.5 of them will be selected for every MOD layer. That works quite well. And it works better than the 50% capacity, where it utilizes the number of parameters better, as seen here. So you have this loss curve right here, and it utilizes the number of parameters better under, I think it's under the same compute budget. And I think that's why it goes up here, because the compute budget, as you increase the number of parameters under the same compute budget, it won't do as good. So I think that's why it increases. I think it utilizes the parameters better under the same compute budget specifically. And that's seen here as well. So 3 and 4 are from here, from the 12.5 capacity, and 1 and 2 are from the baseline full transformer. And we can see it has a lower loss for the flop count and for the wall clock. So as the flops and wall clock and time increases, the loss for the MOD, for the 12.5 capacity, every other layer MOD model has a lower loss. Now, whether this converges to a better loss, we don't know. I guess we'll have to find out. But it looks like it utilizes the parameters better. Yeah. So you gotta rotate. Yeah, same thing. The MOD performs better than the full model under the same flop budget. So that's shown here as well. That's the big thing that they're trying to point out, that it utilizes the parameters under the same flop budget or under the same compute budget as a full transformer. Now, interesting, and then this is another way to look at it. As you would expect, some tokens are passed through a lot, or they're passed through a lot of layers. They're very important, while other tokens are passed through like no layers. And this is the alternating sequence. So this first layer here is 12.5 capacity. The second layer is full capacity, and then 12.5, full, 12.5, full, and so on. Yeah, so it acts as you would expect. And then here, the router weight, if they use the first strategy, the sigmoid strategy, then 12.5 of the values are greater than 0.5 and 87.5 are less, as you would expect, because that's how you're training the thing. So this is what you would use to sample. If these, yeah, this is just the distribution, but yeah, 87.5 over here. So yeah, it trains as you would expect. The auxiliary loss they add. So you can sample it well. And they show down here that it does sample, the causal sampling does actually work. Or yeah, the autoregressive sampling does actually work, as shown here. So that's nice. Even though I think the softmax still has a bidirectional gradient. One other thing, if you're also thinking, oh, why don't I just add MOE to this? They already beat you to that. Yeah, so they already have mode, which is MOE plus MOD, and they show it does well as you would expect, and it's just slapping on MOE to the feed forward layer. Yeah, they've already done that, so can't write it. It can't do like Mo Mamba. There's already MOE plus MOD. Anyways, that's the paper. I'm interested. Does this actually work as well as they say it does? I'm skeptical of papers lately, so we will see.